Bismillah ar-Rahman ar-Rahim. This video is about this trilogarithm identity that involves 6 trilogarithms. If the magnitude of z is less than or equal to 1, the trilogarithm of z is summation k from 1 to infinity, z to the k over k cubed. If z is equal to 1, we have zeta of 3. A more general definition is this integral u from 0 to z of the dilogarithm of u over u. The dilogarithm itself is minus the integral u from 0 to z of the logarithm of 1 minus u over u. The trilogarithm of 1 is in the identity of interest. The trilogarithm of minus 1 is minus summation k from 1 to infinity minus 1 to the k minus 1 over k cubed. This is 1 over 1 cubed minus 1 over 2 cubed plus 1 over 3 cubed minus 1 over 4 cubed and so on. If all the signs are positive, we have zeta of 3. To account for those minus signs, we subtract double the sum involving the even positive integers. From this bracket, we can take 1 over 2 cubed as a common factor. The outside factor is 2 over 8, which is 1 over 4. The bracket becomes zeta of 3. The trilogarithm of minus 1 is minus 3/4 zeta of 3. To prove this functional identity, we need this integral x from 0 to 1 of 1 over x, the square of the logarithm of 1 plus x over 1 minus x. We evaluate this integral in 3 steps. In the first one, consider non-negative integers k and v. The integral x from 0 to 1 of x to the v, the natural logarithm of x to the power k, can be obtained by using the substitution x equal to e to the minus w over v plus 1. dx is minus 1 over v plus 1, the exponential dw. When x tends to 0, w tends to plus infinity. When x tends to 1, w tends to 0. We can get the integral from 0 to infinity by using this minus sign here. The logarithm of x is minus w over v plus 1, which is raised to the power k. X to the power v is e to the minus vw divided by v plus 1. Note that the product of these two exponentials is e to the minus w. We can take minus 1 to the k over v plus 1 to the k plus 1 outside the integral. The integrand is w to the power k times this exponential, and this is gamma of k plus 1, which is the factorial of k. What is the integral x from 0 to 1 of the logarithm of x squared over 1 minus x squared? Since x is between 0 and 1, we can use the series expansion. 1 over 1 minus x squared is equal to summation j from 0 to infinity x squared to the power j, x to the 2j. We can do integration term by term. We have x to the 2j, so v here is equal to 2j, and k is equal to 2. If we use our first result, we have minus 1 squared, that's 1. We have gamma of 3, that's 2 factorial, that's 2. And then we have the sum of the reciprocals of the cubes of the odd positive integers. So if we have the positive integers, we have zeta of 3, but we need to subtract the sum involving the even integers. So this will be 1/8 of zeta of 3. Without gamma of 3, the result is 7/8 of zeta of 3. With this factor of 2, we have 7 over 4 zeta of 3. In the third step, we obtain our integral of interest. We need to do the change of variables. Y is equal to 1 minus x over 1 plus x. This means that y plus yx is equal to 1 minus x. So yx plus x is equal to 1 minus y. X is 1 minus y over 1 plus y. dx is equal to dy times the derivative of 1 minus y, that's minus 1 times 1 plus y, minus what we have upstairs, 1 minus y, the derivative of the denominator with respect to y, that's plus 1. Then we divide by 1 plus y all squared. In the numerator, we have minus 2. When x is 0, y is equal to 1. When x is 1, y is equal to 0. And we can use this minus sign here to have our integral from 0 to 1. This 2 is here. 1 over x is 1 plus y over 1 minus y. This is the logarithm of 1 minus y, which is minus the logarithm of y. And when we square, we get the square of the logarithm of y. This is dx without the minus 2. We can simplify. This part times that part is 1 over 1 minus y times 1 plus y. That's 1 over 1 minus y squared. We have here the integral in the second step, thereby indicating that our integral of interest is this times 2. 7 over 2 times zeta of 3. We also need a couple of results regarding the dilogarithm, the differential of the natural logarithm of 1 plus x over 1 minus x. We have the reciprocal, 1 minus x over 1 plus x, and then we differentiate this. We get 2 over 1 minus x all squared. And when we simplify, we get that this is 2 over 1 minus x squared. This means that dx over 1 minus x squared is 1/2 d, the natural logarithm of 1 plus x over 1 minus x. The dilogarithm of x is minus the integral of u from 0 to x of a logarithm of 1 minus u over u. Investigate. 1/2 the dilogarithm of x minus 1/2 the dilogarithm of minus x. In the integral representation of this part, we have minus x here, and let's write the integral using the dummy variable of integration v. Now let's do the substitution. V is equal to minus u when v is 0, u is 0. When v is minus x, u is x. 1 minus v becomes 1 plus u, and dv over v is du over u. Combine the integrals. The left-hand side is 1/2 du over u, and then we have the logarithm of 1 plus u over 1 minus u. What is the derivative of this quantity with respect to x? This dilogarithm is minus the integral from 0 to 1 minus x over 1 plus x, ln 1 minus u over u du. The integrand and the lower limit of integration do not depend on x. By the rule for differentiation under the integral sign, this derivative is the integrand with the dummy variable of integration u replaced by 1 minus x over 1 plus x. Then we need to differentiate the upper limit of integration with respect to x. We do something similar to this term. When we combine the results and simplify, we get that this derivative is 1 over 1 minus x squared, the logarithm of x. Let's integrate both sides from 0 to z. On the left-hand side, we take this quantity, replace x by z. Then we have a minus, followed by this quantity with x replaced by 0. We get minus, between brackets, 1/2 of the dilogarithm of 1 minus 1/2 of the dilogarithm of minus 1. The dilogarithm of 1 is pi squared over 6, zeta of 2, and the dilogarithm of minus 1 is minus pi squared over 12. This difference is 1/2 pi squared over 6 plus 1/2 pi squared over 12. This is 1/2 pi squared over 4. If we move this to the right-hand side and multiply by 2, we get pi squared over 4. Then we get double this integral here. Let's use the result at the top of the page. Dx over 1 minus x squared is 1/2 d ln 1 plus x over 1 minus x. Do integration by parts. We have the product. Using L'Hopital's rule, we can show that as x tends to 0 from above, this tends to 0. When we use the upper limit of integration, we have this term here. Then we have minus the integral x from 0 to z of this logarithm times the derivative of this term, which is 1 over x. Compare this integral with this one here. This integral is the dilogarithm of z minus the dilogarithm of minus z. We have this identity for the dilogarithm. The dilogarithm of z minus the dilogarithm of minus z is pi squared over 4 plus the product of these two logarithms, and then we move these guys to the other side like this. Another dilogarithm identity that is needed in our adventure is this one here. I prove this identity by showing that the right and left-hand sides have the same derivative. This means that they differ by a constant, and then we can choose a value of z to show that basically the two sides are equal. The derivative of the right-hand side, this is a constant. Then we have ln 1 plus z over z plus ln z over 1 plus z. And from here we get minus ln 1 plus z over 1 plus z. For the left-hand side, we are differentiating the dilogarithm. We can make use of the integral representation. This, for example, is the integral u from 0 to 1 over 1 plus z minus log 1 minus u over u. The derivative is to take this integrand, replace u by the upper limit of integration. Also, we need to differentiate the upper limit of integration with respect to z. We do the same for this dilogarithm, and we obtain a result that is exactly like what we get on the right-hand side. In other words, the derivatives are the same, and we can check that as z tends to 0, both sides tend to pi squared over 6. Now to the trilogarithm. This difference here can be written as the difference between these two integrals involving the dilogarithm. This integral is written using v. Let's do the substitution. V is equal to minus u. dv over v is du over u. This v becomes minus u. When v is 0, u is 0. When v is x minus 1 over 1 plus x, u is 1 minus x over 1 plus x. Now the two integrals are from 0 to 1 minus x over 1 plus x. We can combine them together. We get one integral, and the difference between these two dilogarithms, we can write du over u as d, the natural logarithm of u. On the previous page, we have an identity for this difference here. So we copy and paste, changing every sign, after also writing this ln u as ln 1 over u. Let's do the change of variables. U equal to 1 minus t over 1 plus t. When u is 0, t is 1. When u is equal to 1 minus x over 1 plus x, t is equal to x. The integral is from 1 to x. U becomes 1 minus t over 1 plus t. 1 plus u over 1 minus u becomes 1 over t. This is t, and this is minus t. 1 over u is 1 plus t over 1 minus t. Let's do integration by parts. We have the product of this function and that function evaluated at x. If we take the limit as t tends to 1, again using L'Hopital's rule, we can show that the limit is 0. We just have this term minus the integral of this logarithm times the derivative of this function of t with respect to t. Here is the derivative. Note that this term is minus 1 over t ln 1 plus t plus 1 over t ln 1 minus t. These two terms appear here with the opposite signs, so these go away. We just have minus 1 times minus 2, that's 2, the integral t from 1 to x, 1 over 1 minus t squared ln t, and then this logarithm here. Recall that we had the following result, which we obtained on the previous page, and which I will write down using t. dt over 1 minus t squared is 1/2 d ln 1 plus t over 1 minus t. Thus, we can write this term as 1/2 the integral t from 1 to x, the natural logarithm of t, d, the square of this logarithm. Integration by parts again, we get this quantity minus 1/2 this integral here, which will require some work to obtain as a function of x. This is what we currently have. The trilogarithm identity of interest has these two terms on the left-hand side, but on the right-hand side, it has trilogarithms and logarithmic functions. The idea now is to process this right-hand side so that we have logarithms and trilogarithms. The integral we are interested in looks like this, which is the integral from 1 to x, ln 1 plus u minus ln 1 minus u, all squared du over u. So this is the integral from 1 to x, ln 1 plus u squared, plus ln 1 minus u squared, minus 2, ln 1 plus u, ln 1 minus u. Note that alpha beta can be written as 1/4 alpha plus beta squared minus alpha minus beta squared. This product here is equal to 1/4 ln 1 plus u plus ln 1 minus u squared minus ln 1 plus u minus ln 1 minus u squared. This difference of logarithms is what we have, and this sum here is ln 1 minus u squared. So from this presentation, it seems that this integral to be evaluated needs that we know this integral. Note that here we have ln 1 minus u all squared, and another integral with the plus sign, and then an integral with ln 1 minus u squared. And this is exactly what is done here. Let's focus first on this integral, du over u, and then we have ln 1 minus u all squared. Integration by parts, ln x, ln 1 minus x all squared. This tends to 0 as x tends to 0 from above. The other term is minus integral from 0 to x, ln u, then the derivative of this function with respect to u, that's 2 ln 1 minus u over 1 minus u times minus 1. Let's do another step. Take 2 times the trilogarithm of 1 minus 2 times the trilogarithm of 1 minus x. This is double the integral of the first derivative of the trilogarithm from 1 minus x to 1. The trilogarithm of u is equal to integral v from 0 to u, the dilogarithm of v divided by v. So the first derivative of the trilogarithm is 1 times the dilogarithm of u divided by u. Do integration by parts. We get this when u is 1 minus x, limit ln u, the dilogarithm of u, as u tends to 1, is equal to 0. Then we have this integral with the natural logarithm of u and the derivative of the dilogarithm. This integral here, written in terms of the dummy variable of integration v, is equal to this difference plus 2 times ln 1 minus x, the dilogarithm of 1 minus x. In this integral, use the substitution u equal to 1 minus v. When v is 1, u is 0. When v is 1 minus x, u is x. V is replaced by 1 minus u, and 1 minus v is replaced by u. This integral here is exactly like what we have in the first step. The integral u from 0 to x of ln 1 minus u all squared divided by u is 2 times the trilogarithm of 1 minus 2 times the trilogarithm of 1 minus x plus ln x, ln 1 minus x squared. Then we have this term involving the dilogarithm. To obtain the integral with a plus sign, we do essentially the same steps. Du over u is d ln u. We do integration by parts. Study this difference of trilogarithms. This is double the integral from 1 over 1 plus x to 1 of the first derivative of the trilogarithm, which is equal to the dilogarithm of u divided by u. Then we do integration by parts. We get this integral expressed in terms of both the dilogarithm and the trilogarithm. This integral here, written using the dummy variable of integration v, If we use this exchange of variables, we get this one here, allowing us to write this integral using the trilogarithm, the dilogarithm, and the natural logarithm. We also need the integral in which the argument of the logarithm is 1 minus u squared. We can obtain it using this result. First, rewrite the result, replacing x by x squared. Every x here on the left or right hand sides is replaced by x squared. So we get this relation here, and the integral is written in terms of v. The next step is to use the substitution. V is equal to u squared. This v becomes u squared. dv over v is 2 du over u. When v is 0, u is 0. And when v is equal to x squared, u is equal to x. So we get this integral here, and we have the factor 2. We can divide both sides by 2 to get this integral here. The integral that we need to prove our trilogarithm identity is an integral that has the square of this logarithm. But this square can be expressed using this square, that square, and also this term here. Let's now combine the results so that we get the integral of interest. These are the results from page 4. 1/2 the logarithm of 1 plus u over 1 minus u all squared. This is what we have in the integral of interest. This is 1/2 the difference squared, which is 1/2 this guy squared plus 1/2 this guy squared minus the product. Len 1 plus u, len 1 minus u. 1/2 len 1 minus u squared, then all squared. This is 1 minus u times 1 plus u. The logarithm can be written as this sum. And when we square, we get 1/2 len 1 plus u all squared plus 1/2 len 1 minus u all squared, and then the product again. If we add, we get that 1/2 len 1 plus u over 1 minus u all squared plus 1/2 len 1 minus u squared all squared is equal to len 1 plus u all squared plus len 1 minus u all squared. These guys go away. Take every term here, divide by u, and then integrate from 0 to x. We need this guy, and as we can see from this line, it is expressed in terms of the 3 integrals that we have already obtained on page 4. Here is what we currently have. It is messy. We have trilogarithms, dilogarithms, and logarithms. In order to simplify, we will try to express the dilogarithms using the dilogarithm of x and the dilogarithm of minus x. The reason for this is that our formula for the trilogarithm has the integral and the difference between these two dilogarithms multiplied by len 1 plus x over 1 minus x. So the hope is that if we express every dilogarithm using these two guys, perhaps some cancellation will take place and we end up only with trilogarithms. But can we achieve our objective? The good news is yes. We have dilogarithm identities that will allow us to move forward with our plan. Specifically, we have these dilogarithm identities. The first one is proved in this video, and these two have been proven in a previous video. This second identity will allow us to express this dilogarithm in terms of the dilogarithm of x. What about this one? Use the same identity after replacing each x by x squared. And when we do this, we are able to write down the dilogarithm of 1 minus x squared in terms of the dilogarithm of x squared. But the dilogarithm of x squared from the third identity here is double the sum of the dilogarithm of x and the dilogarithm of minus x. The first identity is what we can use to replace this dilogarithm by the dilogarithm of minus x. We have our integral, we have the dilogarithm identities, we make use of them, and then we simplify. We end up with 4 trilogarithms. The dilogarithm of x is multiplied by len 1 minus x plus len 1 plus x minus 2 len 1 minus x. So this is len 1 plus x over 1 minus x. The dilogarithm of minus x is multiplied by len 1 minus x plus len 1 plus x minus 2 len 1 plus x. So this is minus len 1 plus x over 1 minus x. The negative of this, the difference between the two dilogarithms, is multiplied by this quantity here. From page 3, we have this difference of trilogarithms expressed in terms of the dilogarithm and this integral. This integral is from 1 to x, but the integral that we have obtained on the previous page is from 0 to x. The integral from 1 to x is the integral from 0 to x minus the integral from 0 to 1. And this is the very first thing that we have obtained. The integral itself is 7 over 2 times the trilogarithm of 1, which is zeta of 3. Those are the terms that we obtain for the integral from 0 to x. We need to subtract 7 over 4, the trilogarithm of 1. This is our result for this integral times 1/2. The dilogarithms disappear, and we end up with an expression involving these two trilogarithms on the left-hand side, these four trilogarithms on the right-hand side, in addition to these two terms.